When you're trying to shave milliseconds off your application's response time, you'll eventually arrive at a crossroads, Redis or Memcached. But looking for a winner in a speed test misses the point. Both systems serve data at sub-millisecond rates. To achieve that level of performance, both systems use the same foundational trick. They bypass slow disk storage entirely and keep your entire dataset in RAM. The choice actually hinges on architectural philosophy. One system is built for specialized, predictable efficiency, while the other functions as a versatile, multi-purpose data server. Your decision comes down to aligning the technical trade-offs with how your application layer consumes data under load. Memcached treats all data as flat, opaque strings. It doesn't know or care what is inside the object you're storing. This means if you want to store a complex object, like a user profile or a shopping cart, your application has to serialize that data into a string before writing it, and then deserialize it every time it reads it back out. This creates a challenge when you need to update just one piece of that object. You have to fetch the whole string, change the value, and write the whole thing back, a cycle that can lead to race conditions where one user's update overwrites another. Redis recognizes native data structures like lists, sets, and hashes directly on the server. You can tell Redis to increment a single counter inside a hash, and it handles it in one atomic step, without the need to pull the full object over the network. The trade-off is overhead. Tracking the metadata for those rich data structures means Redis requires more memory for every key compared to a plain string in Memcached. Memcached requires the application to do the data shaping work, while Redis acts as a computational engine that manages the structures for you. When operating entirely in RAM, the way a cache allocates physical memory determines its stability and the likelihood of a crash under load. Memcached uses a memory model called slab allocation. It divides memory into 1 megabyte pages, and then slices those pages into a grid of perfectly equal fixed-size chunks. Because these chunks are pre-allocated at a rigid size, data drops into its slot predictably. This prevents external memory fragmentation. You don't get unusable gaps between objects. But there is a hidden cost. If you store a 60-byte piece of data inside a 100-byte chunk, those remaining 40 bytes are essentially trapped. This is internal fragmentation. Redis uses dynamic memory allocation. It shrink-wraps the memory boundary to fit the exact size of the data, down to the byte. However, as objects are created and destroyed, this exact fit strategy leaves microscopic gaps across your RAM. Over time, these gaps accumulate, causing external fragmentation. Memcached provides a predictable memory layout by accepting wasted space inside the chunks. Redis optimizes for an exact fit, but requires active background defragmentation to keep those gaps from affecting performance. Memory layout keeps you stable, but threading determines how the cache survives heavy traffic spikes. Memcached is inherently multi-threaded. This allows it to scale vertically, saturating every available CPU core on a single host to handle high volumes of concurrent raw throughput. In contrast, Redis executes commands on a single-threaded event loop, meaning it processes operations sequentially. This single thread provides a significant benefit: strict atomicity. Redis can perform complex updates without the latency penalty caused by locking and unlocking resources across multiple threads. But there is a vulnerability. If you execute a single slow command, like scanning a set with 10 million members, it will block the thread, stopping all other operations until it finishes. Memcached prioritizes sheer concurrent throughput. Redis trades that vertical concurrency for guaranteed data safety during complex operations. When RAM reaches capacity, these systems must evict old data to make room for new entries. Maintaining a perfect chronological list of the least recently used keys requires a doubly linked list, which adds a 24-byte pointer overhead to every single key in the cache. To avoid that overhead, Redis uses approximated LRU. Instead of a heavy linked list, Redis embeds a 24-bit clock timestamp directly into each object. When memory is full, it samples just 5 random keys, checks their timestamps, and evicts the oldest of that specific sample. This approach saves significant memory, but you accept a margin of error. It may occasionally delete a slightly newer key because the absolute oldest item wasn't in the random sample. Memcached uses a different approach called segmented LRU. It divides memory into hot, warm, and cold queues. Background threads move data between these segments based on age and activity, keeping the read path clear and avoiding locks. At scale, intelligent eviction is about minimizing the CPU and memory costs required to find data that is eligible for deletion. The architectural choice depends on your specific workload and how much complexity you need to handle server-side. If your primary goal is a read-heavy workload consisting of rendered HTML, API payloads, or standard serialized objects, then Memcached is the standard choice. Utilizing all available CPU cores on a single node is the priority here. This route means your engineering team takes full responsibility for data formatting and must be ready for total cache loss if a server reboots. But if you require atomic counters, live leaderboards, rate limiters, or the ability to survive a crash, you should choose Redis to leverage its native data structures and disk persistence. In this case, you will need to monitor memory fragmentation and eventually shard the database horizontally once you hit the processing limit of a single thread. Memcached is a highly efficient memory cache, while Redis is a complete in-memory data structure server. Design your infrastructure based on which of those rules your application actually needs.